start. And as Tanda said, I just intended to do something very simple or elementary, but something quite nice, and that will be doing some sums and discovering Bernoulli numbers along the way, which means that we are going to see those numbers pretty a lot, and maybe it will be sufficient to dispel some air of magic around these numbers, because many people encounter those numbers just in passing, and then they think, oh, it's just another series of weird magical numbers. I don't know anything about them. And they have some very nice properties, and we will discover them as we go. So that's the point of this talk. And now maybe let's start with the simplest thing. Yeah. Je tady nějaký lepší mazadlo. Aha, a jo, toto je ono. Super. Yeah, great. We wipe out this and let's start. So the first thing I would like to do here is to build some very basics of finite difference calculus and summation calculus in parallel with the classical differentiation and integration that we all know. And there will be a ton of similarities, so I think it's worthwhile to do it that way. And let's just start by showing what I mean by those finite differences and sums. So if I have some function, let's say f, or I should write n, then its finite difference would be just, I will use this triangle symbol for the finite difference, and I will define that as fn plus 1 minus fn. So there you get it. The name finite difference is quite clear, I think. And it's just difference of the function in the two neighboring integers. And just as we have integration as an antiderivative, we can do an anti-finite difference. And that would be some sort of indefinite sum. So let's denote it just by this sign. For now, we will just use only this, and we won't put any bounds here, and we will just say that if we use this sum operator on the finite difference, then they will just cancel out and we get back the original function. So you can see that this is entirely parallel to the definitions in calculus, where you have the derivative and the integral is just an antiderivative. So the only difference is the size of the step here. So here, when we take derivatives, the size of the step is infinitesimally small. Here it's just 1. And that's the main difference and pretty much the only difference between these two things. So we will expect that many of those rules and results will be quite similar. And it is like so. So let's just start deriving some very simple results. First of all, if we just take finite difference of a constant, say like this, then we will obviously get a 0 because, well, the constant is the same in both points. So this is just analogous to the case with the derivative. Now, if we do this to n, where by n I just mean function fn equals n, I will use n just as the general variable in here. Then we get n plus 1 minus n. So those n's cancels, and we get a 1. And we can follow through with some higher powers. Here we would get n plus 1 squared minus n squared. And when we expand this according to the well-known formula, the n squared cancels and we get 2n plus 1. And in similar way, we can get that the finite difference of n cubed would be 3n squared plus 3n plus 1, and so on. So as you can see, the results are pretty similar to what you get with differentiation. Here we get a 1 as well, and if we differentiate x squared, we get 2x, which is sort of the same as we get here, but we get some more terms. And that's the same thing with the other powers. And so on. So as we can see here, the size of the step, the finite size of the step, will incur some more terms in here, and it will be just more mess. But still, it looks pretty tractable. Okay, go away. And when we have a couple of these, we can also invert them to get some of the rules for sums. So let's do that. We'll get rid of this. So one thing that is pretty obvious as well is that if we sum a 0, we get any constant. And that is just the same thing as with integration. So here, the indefinite summation gives some sort of primitive function. And when we do definite summation with some limits, then those primitive functions just subtract one from another. So there can be arbitrary summation constant. This is just the same thing as with integration. And we can continue. So here the difference of n was 1. So the sum of 1 will be n plus a constant. Here it will be a bit different. We get sum of 2n plus 1 equals n squared. So if we want to extract the sum of n from this, then we just have to split the sum a bit, like this. And now we can just express the sum of n, because we already know that this thing is just an n. So we get the result that Gauss already knew in kindergarten. This is the famous formula for the sum of first couple of integers. Of course, we have to add another summation constant. And in this way, we can proceed and get more and more of those results. And just for the sake of argument, let's do one more, because everyone knows how to derive this thing by tons of different ways. But doing the same for the sums of the squares, it's not that easy. And there is no geometrical, let's say, trick to guide our way. So it will be nice if this very simple thing will give us the right formula, and it will, because we see that sum of this needs to be n cubed. So we do n cubed equals sum of 3n squared plus 3n plus 1, which is 3 of those sums n squared. Then we get 3 times sum of n, but we know that already. And sum of 1, that's just n. A constant, of course. So here we just express the sum once more. And we get n cubed over 3, because there was a 3 in here. plus n squared minus n over 2, because those 3's will cancel, and of course a minus. And here we get n over 3. Of course, a summation constant as well. And now if we just put everything together, we will get the very famous formula for this sum, and that is n minus 1 times 2n minus 1 over 6, plus a constant, of course. So even with this little, we are already able to deduce those formulas, and they are not really that much trivial. So this is already a good achievement. But let us continue. We can do much more with this. And of course, one simple thing that could be done is using some geometrical series. So let's do that. And that will be even simpler, because if we have, well, I'm writing in the shadow, so let's do it a little lower. If we do a difference of x to the nth, then we just get x to the nth plus 1 minus x to the nth, where x is a constant. So if it's a constant, then we just can take it out, and we have x to the nth times x minus 1. But this is, of course, a constant. So if we send it to the other side, we get that the difference of x to the nth over x minus 1 is just x to the nth. So we get that the sum of x to the nth is just this thing, x to the nth minus over x minus 1. So in this way, it's just like before. We did some very, very simple things, and we get the formula for geometrical series. And when we have this thing, then we can follow up with more, because we can do a little bit of a complex numbers trick by putting, let's say, x equals e to the I phi. So if we do that, we get e to the I n phi sum that equals e to the I n phi over e to the I n phi minus 1. And if we want, we can multiply this thing by some constant like this, and then it appears here. So let's just make some calculations here. Here I will take out e to the I phi half, because what appears in this bracket is just 2i sine phi over 2. So by doing this, we can put this in the numerator and get e to the I n phi plus alpha minus phi half over 2i sine phi over 2. And by this, we get formulas for summing sines and cosines, which is pretty nice, considering the amount of job we have done, which is next to nothing. So if we just write this as a cosine n minus 1/2 phi plus alpha plus I sine of the same thing, then we can sum a sine of such a thing. And we do this just by getting the imaginary part of that thing. So that is minus a cosine over 2 sine phi over 2. And that's a cool result. We can do the sum and the same thing for the cosine. Just get the real part, the i's cancel, and we get this thing. And by the way, if you remember the formulas from calculus, then you get the integral of cosine x phi plus alpha, let's say, x, then we get a sine of the same thing minus over phi. If you compare it to that formula, then it's pretty similar, right? So I think it's obvious how those two things can be built really in parallel, one to another. So let's stop with sines and cosines for a little bit, and let's build a bit more of theory, because one of the very useful things that we have in calculus is, of course, the Leibniz rule, which is the product rule for derivatives. So when we see that the finite differences and derivatives parallel each other so much, and it would be quite obvious to think that there should be a Leibniz rule for the finite differences, right? And of course there is, and let's see how it goes. So with derivatives, we have, of course, this thing. And if we do that with a finite difference, then it will give pretty much the same thing with one little catch. So let's just write it out by definition. So we need to get the product in n plus 1 and subtract the same thing in n. And here I will just proceed in the same way as I would if I was deriving the Leibniz. Just let's add and subtract one of terms that would look like this, let's say. Of course, that didn't change anything. So this is the same thing as before, but if we look here and here, then we can take out the fn plus 1, and gn plus 1 minus gn is what remains. So that is the finite difference. And in a similar way, let's put these two together, and we can take out the gn, and fn plus 1 minus fn is what remains. So that is the finite difference of f. So you see the parallels. It's really just the same thing. And the one little catch is that here we have the plus 1. And that's something that is connected with the finite size of the step, right? Because here the step was infinitesimally small. So yeah, we just don't need to care about that. But here we do. But aside of that, this is just the same thing. And of course, when we have a Leibniz rule, we can sort of invert it to do some sums. Because, of course, we have integration by parts. So if I have such an integral, then I just add to it the other term and subtract it again to make this a total derivative of fg. And by this, I get the very well-known rule of integration by parts, and we can expect just the same thing happening with sums. And of course, it works with sums, and the process of deriving it is just the same. So if I have something like f times finite difference of g, and I will need to be more careful about those arguments. Oh, well, maybe I will just rename these two to put this +1 into the g, which doesn't change anything because the whole thing is symmetric, but it will be a bit nicer. And now I will just add and subtract that term. Add it and subtract. And of course, this is still the Leibniz rule, and the sum and the finite difference will kill each other. So we get f times g in n and subtract the sum of gn plus 1, which is important, times the finite difference of f. So we have just the same summation by parts as we had in the integration by parts, and it's quite obvious. By the way, this thing is sometimes called the Abel transformation, but that sort of obscures the substance of this thing. It's just summation by parts. So here we can really see how it builds up very similar. And I will do one more little thing and move along. We can also use this for some, let's say, approximate calculations. So if we do a sum of a logarithm like this, then of course we get something like logarithm of 1 plus logarithm of 2 plus and so on, up to the logarithm of n plus 1, n minus 1, or whatever. So here the primitive function should be something like this. But this is not something that we would like to mess with. So just let's use this Thiering's formula. Here we would get n minus 1/2 logarithm of n minus n plus a constant. And that logarithm of square root of 2 pi can be just put in the constant. And here we can do something like this, for instance. And this is not really a trivial thing, because if we would exponentiate this expression, we would get something like 1 to the first power times 2 to the second power, 3 to the third, and so on, up to n to the nth. And this thing is called the hyperfactorial, which is not to be confused with the superfactorial, which is an entirely different thing. So don't confuse them. But if we calculate this, then we can get some estimate on this thing. And we can do that. We can use our newly found summation by parts. Do that. Let's say that this thing is the f, and this is the difference of g. So here we get just a 1 by doing the difference, and here we will need to do the summation of that logarithm. But that's not that hard. because we already did that in here. So we have n minus half logarithm of n minus n. So here we get product of those two things, which is n minus 1/2 logarithm of n minus n squared, and then we subtract the sum of product of these, but this has to be taken not in n, but in n plus 1. So here we get something like n plus half logarithm of n plus 1 minus n minus 1. So what we can do here, and I should say that this is only an approximation. When we are already approximating things, then why just not continue? And why just like this? We have just taken out the n. And this, let's say, we will want to expand that and say it's approximately 1 over n. So we can just copy these things. Here we get plus sum of n, which is n minus 1 over 2, and plus sum of 1, which is n. And then we have minus sum of n over n, and we will ignore the 1/2 over n. So that's another n, but with a minus, and then we get n log n. And now we can do the trick that every first-year student hates, which is just seeing that this is the same thing that we wanted to calculate in the first place. So we just can express that, and I won't be just going through that very carefully and write the answer, if I will find it. Now, if we do that, then we get this thing. Is approximately equal to 4n squared minus 4n plus 1 over 8 logarithm of n minus n squared over 4 plus a constant. So this makes it possible to just estimate the hyperfactorial. If we just exponentiate the thing, we get some pretty good estimate, because now if we want to do the real hyperfactorial, we would need to put some limits on that, like this. And of course, that we have just the same, quote, Newton-Leibniz formula that we had for integration. So if we do this, then we just need to subtract the primitive functions. So the only problem is that we need to subtract the primitive function in one above the upper limit. And here we just use the lower limit. And that's because if we put that in this way, then the sum will telescope nicely. It would be perhaps good if I just showed it like this. If we had sum of sum, let's say, fn, and sum from a to b minus 1, then we can just use the primitive function to write the Fn as such a difference. And of course, we have f in b minus 1 plus 1, and then all of those just cancel, and the only thing that remains is the last part, which is minus f of a. So if we do that, then we finally arrive at a very, very nice approximation, which is, let me write it down, that, oh, I already did here, so let's just write it. 4n squared minus 4n minus 1 over 8 plus 0 with plus 1/4. And if we compare this to the real asymptotic formula, then we will see that this is really close, because if we exponentiate this and we get this hyperfactorial thing, then we just get n to the power of this weird fraction minus this, oh, I mean times, and here we have e to the 1/4. And the real thing would be that it is asymptotically equal to some a, which is some weird number called the Glaisher-Kinkelin constant, just a weird constant. And here we should have n to some other weird fraction, which is not very different from ours. And here e to the minus n squared over 4. So when we compare, then really this is just the same as this. And the e to the minus n squared over 4 is just same as this. So the only difference is this n to the 1/8 as opposed to n to the 1/12 and this weird constant. But oh, I will just need to look it up again. But this e to the 1/4 is approximately 1.2840 and so on, while this Glaisher-Kinkelin constant is approximately 1.2824 and so on. So this is really close, and we did just some very elementary approximations. This really, it has been high school math. We had to use no tricks, no weird analysis, just very simple things. And we get so close. So I think that's quite remarkable. But now let's just finish with this for a moment. And let's meet the Bernoulli numbers, because that's what's in the title of this talk. So what we will now want to do is to sort of return to the very beginning, when we were calculating sums of n squared and n cubed and so on. And we will just want to do more and more of them. And we will want to see if there is any system in it that we could take advantage of. And it will turn out that there indeed is some regularity. And we will show what it is. So now, for a moment, let's abandon what we did before, the notations, and I will use such a notation. Here we go from 1 to n instead of from 0 to n minus 1, just because the calculations are a little bit nicer. So these are just the sums that everybody knows. So S0, oh, I mean Sn0, that's just sum of n ones, so that's an n. This is the famous thing that Gauss knew in the kindergarten. So that's n plus 1 over 2. And this we know as well. And I will just write this like n squared over 2 plus n over 2. And here, if we expand that fraction that everyone remembers, then we get n cubed over 3 plus n squared over 2 plus n over 6. And so on. Many people remember this as well, because it's just the square of this. And so on. So here we get some polynomials. The degree is just one higher than the power that we are taking. And then there are some weird coefficients. So how do we know what coefficients to put in those polynomials? And that's the thing that the Bernoulli numbers will help us with. Get rid of this. And in order to get that, we will write an equation for this one. So apparently, if we just do such a difference, can you see it? Yeah, good. Then what we are left with is just the last term, which is n to the k. So that's very nice. And now we can help ourselves a little bit by using calculus and differentiate. So if we do that and differentiate with respect to n, then we get just k n to the k minus 1. So what we get here is that if we differentiate that Sn, then we get something that needs to behave like the one lower Sn. So here we differentiate it, and the difference equation has a k minus 1 in here. But that was kind of the difference equation that S with k minus 1 was satisfying. So in this way, we can hope to build up from the lower ones to the higher ones. And of course, so with this, we can see that Sn with the power of k differentiated will need to be something like k Sn to the with the powers of 1 less. And that's not everything, because we had such a difference equation in here. There can be some summation constant. So let's add it now.
Sorry, can you change your pen?
Okay.
Becoming really invisible.
What about this? That should be good, at least for now. So here we can just integrate and get that this Sn with powers of k is k times integral of the previous one with respect to n. Then we integrate this constant with respect to n, so we get the constant times n, and then we get an integration constant. We call that d. And now we just do a couple of very simple arguments. So first off, if we do S0 of anything, then we just go from 1 to 0, and there is not even one term in that sum. So we will clearly need that S0 of anything is 0. So if we look at this, here we had some polynomial. We integrated it. So this integral contains only powers of n and not any constants. Here we have a power of n as well. So if we plug in n equals 0, this has to go away and this has to go away as well. So the only thing that is remaining there is that integration constant, but we want it to be 0. So in fact, this thing won't be here. It's just a 0. And then there's another problem. We had some unknown summation constants, ck, and we don't know anything about them. But we can get some information by realizing that if we sum from 1 to 1, then we just get 1 to the k. So that's a 1. And now if we plug that 1 into this, we will get some known coefficients here in this integral. And the only thing that is not known is this ck. So we can just get its value by just saying that it needs to sum to 1 with all the other coefficients. So that's quite a nice thing. And now we can try it out. For instance, let it be for a while. We had that S1k equals n plus 1 over 2. So let's see what's S2. Oh, I mean, I'm sorry, I just messed up these indices. I mean Sn. First powers, I'm messing it up again. Good. So we can get this by just multiplying by k, which is 2, and integrating the previous one. So here the 2's just cancel, and we have integral of n squared plus n dn. Then c2 times n will go there, and the integration constant was 0. So this is it. Now we can do the integration. We get n cubed over 3 plus n squared over 2. And now we get something times n. So we need all the coefficients to add up to 1. So here we have 1/3 and 1/2, which is 5/6. So the number here needs to be 1/6. And hence we know that C2 is 1/6. And we can go further and further with this. So to get this, we integrate again, multiply by 3. So here we multiply by 3, then integrate and get n to the 4th over 4. Here we have 3 over 2, and then n cubed over 3. So just get rid of this. Here we get n squared, and here we multiplied by a 2, so by 3, so a 2 was left down below, and we have this. And then we have, of course, C3 times n. And here we have 1/4 and 1/2 and 1/4. So that's already exactly 1. So the C3 is at 0. And we can still do more, and I will just do one more pretty quick, because everyone knows this, but the next ones are just not really trivial to derive or memorize or anything. So here we multiply by 4 and get 2. I mean this. Here we multiply by 4 and get this. Then the next one is not there, and then we have C4 in here times n. And what's this C4? So if we just add up all those coefficients, oh, I mean 1/3, then, well, what do we get? We will need to do 30ths of them, and this is 6 of them, this is 15 of them, and this is 10 of them. So here we get 31 30ths, and so this C4 needs to be -1/30th. So that's a pretty weird number, right? But that's what it is. And here we can just see the pattern. The only thing that is really important are those C's. And then all the other coefficients are just made by repeated multiplying by those numbers and integrating over and over again. But all of those coefficients, in fact, come just from those C's. And that's just one sequence of numbers. So when we've done this, then we can just take it a step further and do a general case. And that will be easy if we just realize what's multiplied by what and integrate it how many times. So, or maybe let's look here. So if we have something like Sn with the kth power, and we want to know which coefficient is at n to the pth power, let's say, then how this came to be. First of all, some time ago, it had to be just first power of n with the appropriate coefficient, and then it had been integrated k minus p plus 1 time, minus 1 times to get it to n to the p. And each integration adds first a 2, then a 3, and so on. And lastly, the p minus 1, the p minus first integration will give a p in here, in the denominator. But we also multiplied by some numbers. So if this was first to be seen in sk minus p plus 1, then the next number is k minus p plus 2. And the next one is k minus p plus 3. And so on and so on. And the last one is a k. And of course, we need to carry the coefficient, which is c with k minus p plus 1. So this expression is what eventually builds up at each of those powers. And now we just can simplify a bit. Just keep the coefficient, and these work products will be best replaced by factorials. So here we have k factorial over the first that is not in there, so that is k minus p plus 1 factorial. And here in the denominator, we also have a p factorial. And that's pretty nice already, but let's just add a k plus 1, because these two sum to k plus 1. So it will be nice to borrow a k plus 1 like this. And then we have k plus 1 factorial on the top. So we can write that as k plus 1 choose p times n p. So this is the formula for any of those coefficients. And now if we just want to know the whole Sn, then we just sum them together and that's it. So in this way, we can already find pretty much any of those formulas just by knowing a bunch of those weird numbers. And I will just look at it here because I don't want to mess up. So we have, by summing, we have this one. This can go in front of the sum, and here we need to sum through all of those powers from 1 to k plus 1. And we get all of those k plus 1 over p, choose p. And this can be just rewritten like this. And this is pretty much the formula. We can make it a bit nicer just by switching around the k, or I mean the p. And we will just put, instead of p, we will put k plus 1 minus p, just to make it a bit nicer. And we get Sn to the k is 1 over k plus 1. Here we sum from 0 to k. And now the binomial coefficient doesn't care about that. So we can write it as it is. Then we pretty much replace the index on the c, and here we replace as well like this. So we have this one. And that's the formula. And now we can just return to our previous ways and start working with the sums that go from 0 to n minus 1, because we built our whole theory around that. So we can do something like p from 0 to n minus 1. I mean p to the kth. And now everything we've done here is just subtracting the last term, which was n to the k. So we can just copy this whole expression. And the only thing is that n to the kth power will be different. Minus n to the k. And as you can see, this n to the kth hits only one of those terms in the sum. And it is the term that has p equals to 1. Because here we have k plus 1 minus p, so the p has to be 1. So here, the only thing that this actually did is modifying this C1, because P was 1, by subtracting a 1 from it. And since the C1 is a 1, is a 1/2, which we can see if we just repeat the formula that goes in the kindergarten. So here we have the plus 1/2. And now we subtract the 1. And we get something a little bit different, which is minus 1/2. So let's just use these numbers that are just equivalent to the C's, except for the C1, which will be minus 1/2 instead of plus 1/2. And let's call them just some random name. Let's call them Bn, right? And when we do that, we can just get rid of this minus n to the k, and we can replace those c's by our b's. And we are done, because this thing that we have here, this is called the Bernoulli formula, or Bernoulli-Faulhaber formula. Although historically, Faulhaber hadn't really discovered this or the Bernoulli numbers. Now, of course, now when I've just used totally randomly the letter B for this, it was obvious that this was going to be the Bernoulli numbers, right? It's just them. The Bernoulli numbers come about in this formula when we try to sum different powers of natural numbers. And we just need to know the Bernoulli numbers to be able to sum any kind of such sum. So that's pretty nice. And this is why the Bernoulli numbers come out everywhere when there is some summing or something like that. Because they just started this way, being some coefficients of some sums, and then it's not really surprising that when we sum things, then we get Bernoulli numbers. So these Bn are the Bernoulli numbers. And now when we know what they are, we can just write down some of them. B0 is just a 1. That comes from the fact that if we sum n once, we get an n, so the coefficient at n is 1. B1 is minus 1/2. We just did that a little bit before. B2 is just equal to the C2, and that was 1/6. We have here still. B3, that is still the same thing as C3, which is a 0. B4 is minus 1/30. B5 is a 0. B6 is plus 1/42. B7 is a 0. B8, that's minus 1/3. Oh, I'm sorry. That's okay. Yeah, it is true. It's minus 1/30. B9 is a 0. B10 is 5/66. And those denominators get pretty wild, but get the idea. Here we have something like, oh, it's 691/2730, I think. Just a weird fraction. I just tore off my mic. B13 is a 0. B14 is 7/6, and so on. This is a 0, and we can continue like that. So here it seems that those b's are just some small weird fractions. That's not true at all, as we will see shortly. When we just attach this thing once again. But there is one more thing. As we see, the B1 was minus 1/2, but then every odd B was a 0. Well, is that just by chance, or is it some pattern that we can see? And that's the question that we will answer right now. But before that, we will do one more thing, and that is that we build a generating function for those Bernoulli numbers, because studying such sequences using generating functions is oftentimes the best we can do. But first, we will need to make a recurrence for those Bernoulli numbers. So let's do one, and I will want to put n equals 1 in this formula. So here the sum has only one term, and that's a 0. If I put n equals 1. So here we have a 0, and here we have 1 over k plus 1, and the sum goes here just verbatim. Oh, I messed up this index, and n is just a 1. So this is a recurrent equation that the Bernoulli numbers need to satisfy. Of course, with the initial condition that b0 equals a 1. And just from this recurrent relationship, we can get all the Bernoulli numbers, as many as we like. So that is quite important. Let me just wipe out those numbers. So I will just make this a little bit nicer, because we have a 0 in here. We can just ignore this fraction, and I will want to write it in a bit different way, maybe. Just doing this. I will just mess up the indices a little bit, just putting n minus 1 is instead of that k. I mean k and k here. So this has to be a 0. And you see that this sum is kind of incomplete. The last term, the nth term, is missing. And that will be quite useful, or it will give us a hand when we derive the generating function. So I was talking about generating functions now, and I didn't really say what they are. So essentially, a generating function of some sequence is just a function, a power series that contains the elements of the sequence as the coefficients of the individual powers. So here, it will be nice if we do the generating function like this. We will sum from n to infinity, and here we will want that the coefficient is the nth Bernoulli number over n factorial times z to the nth. And now this z is nothing in particular. It's just a variable that helps to keep those coefficients apart, because we can tell them apart just by looking at the different powers of that z, but it has no, quote, real significance, no real meaning. So let's see what this function is. And I've just put this and factorial in here as if by just some random idea. And it's not random at all, as we will see, because there are several types of those generating functions. And this will be the most useful, because every time when we have recurrences that contain these binomial coefficients, it's just better to use the functions that have that factorial in here. And I will just show why, because if we have two such generating functions, let's say f, which is sum just from 0 to infinity, I won't repeat that. And here we have some Cn over n factorial times Zn. And then we have a G, which is similar series. Then if we multiply them term by term, then we get this. We get f times G equals, oh, there's too little space for that, but here essentially we do the two sums here from n, and the other will be k, let's say. And here we have c and d k over n factorial k factorial times z to the n plus k. And it will be good to just get rid of one of those variables. Let's say get rid of that k. And instead of that, let's put L equals n plus k, just to get all those powers apart, one from another. So let's do that. And we get this. So we get L going from 0 to infinity. Here we have Z to the L because that's just the sum. And then we get rid of the K, and that N is left, and that N needs to be going from 0 to L, because that K that we got rid of just can get varying values, and we need to cover them by doing this. If we just make a little picture, then it will be very clear, I think. If we have n here and k here, then if we do such a substitution, then we are just something like this. And of course, we need index for those, but as well, we need indices to cover us going through those lines. And that's just that n that goes to L. And here we get C and D K, which is L minus n over n factorial, L minus n factorial. And here we see why it's so great to use that kind of function, because if we want to express the product as the same kind of the function with the factorial in the denominator, then we just add it here, and we get the binomial coefficient just like that. So we have this, and here we have sum from 0 to L. Here we have just L choose n, C n, D n, L minus n, and I will just clear this because before it just confuses the heck out of you. Let's get rid of it. Get rid of this as well. So this happens when we multiply two generating functions like in this form. And that's great because we have the recurrent relationship just in such a form. Here we have the binomial coefficient, which is just the same as we have here. Here we have the B case that will come from the generating function that we don't yet know. And then what's remaining is some ones. And to be precise, here the sum is going from 0 to n minus 1. So the D's need to be ones for n from 0 to n minus 1. And the last one needs to be a 0. And since we are going in the opposite direction, that means that the D0 needs to be a 0. And all the other coefficients need to be a 1. So, of course, if we have this kind of function, we all know it just sums to the e to the z. And if we want to get rid of the first coefficient, then, well, that's just a 1. So let's get rid of it. And that's it. So now we can make use of this multiplication rule and of that recurrent relationship to get the function. And here it is. So we multiply the unknown generating function by this function that has all the ones except the 1, 0 that we need to construct that sum. And this is equal to well, what? So this relationship works only for n is greater or equal to 2, because otherwise we just have the initial condition be 0 equals 1. And if we would do this for n equals 1, then we would get 1 over 0 b0 equals 0, which is not what we want. So this works only for n equals to 2 or higher. And because of that, there can be, on the right-hand side, there can be no term with z squared or any higher power, because all of those coefficients need to be 0. Just because we constructed by this multiplication rule, this thing in this. And what remains is, well, the 0th power, which means there is sum from 0 to -1, so that's nothing. And at the first power, there is just 1 choose 0, b0 times z. But b0 is a 1, and this is 1 as well. So we have a z on the right-hand side. And now it's just a matter of simple division to get the generating function. So in fact, if we take this function and just make Taylor series out of it, the individual coefficients will be exactly equal to the Bernoulli numbers over that factorial.
So if you repeat all the higher powers of that.
Oh, right. So let's do it a little slower. We will use this rule for doing this product. So I just repeat this. Oh, L, of course. And so here we have L choose n. The C's, let's say they are coming from the generating function. So we get the B n in here. And then the D L minus n is coming from the e to the z minus 1. So this is 1 each time except for D0. So the D0 is a 0 because we subtracted that 1. And because of that, the term with n equals L, which is what gives a D0 in here, just won't be there. So I can just as well write it like this. And now we just look at this. This is really the same thing. These are just ones, and the one that was 0 is just cancelled already. So that's how it gets in there. And here we get that this is a 0 because of this for n greater or equal to 2. And the only other thing that can remain is just the constant term or the z term. And the constant term is 0, and the z term is just a z. So this is how we get the generating function. And now when we have that in our hands, the real fun can begin, because now we can start to prove nice things about the Bernoulli numbers. Get rid of this. So first of all, we already saw the pattern that most of the odd Bernoulli numbers were 0. And now we would like to know if that's just some random chance or if that's a rule that those numbers follow. And there's nothing easier than just look at that, because we have this generating function. Now we know that the B1 seemed to be the only odd Bernoulli number that was not 0. So if we want to know if the rest is 0 or not, then just let's subtract the term with the b1. And that's the term with the first power. That was b1 over 1 factorial z to the first power. Here, b1 was minus 1/2. So in fact, we have z over e to the z minus 1. And here we have minus 1/2 of a z. So now let's add those up. And we get, let's just take the z out and the half as well. And here we get 2 because of this. And we add e to the z minus 1. So the 2 cancels and only a 1 remains. So we have this result. And now we know that this, in fact, is the hyperbolic cotangent of z12. And how do I know that? I just take out e to the z12. So I get z over 2. Here I have this, of course, with plus. And here I just get twice the cosine hyperbolic, and here twice the sine. So we get that this is z12 cotangent hyperbolic z12. And now if we look at that, well, we know that the cotangent hyperbolic is an odd function. And the z, of course, is an odd function as well. So all in all, this thing is an even function of z. And that means that it can contain only the even powers. So in fact, when we have got rid of that first term with b1, only an even function remains. So all the other odd coefficients must be 0. So in this very simple way, we can immediately prove that. And I think this is quite remarkable because otherwise we would just need to do some lengthy induction. And here it's just very simple. And moreover, by doing this, we already get another nice Taylor expansion that I will just write here because it can be useful. So we have z12 cotangent hyperbolic z12 equals just the generating function without the first power. And since all the others are just 0, then we can write it like this. b2n over 2n factorial z to the 2n. It's just because we already know that the odd terms aren't in there, and we got rid of the last one that wasn't 0. So we just can sum over the even ones. And when we have this, of course, we can extract number of other useful expansions. So for instance, first let's just put z equals 2iw, where w is some new variable. So here we have iw times cotangent hyperbolic iw. But if we have cotangent hyperbolic of I times something, then we get minus I on the outside, and the cotangent just changes to a normal cotangent. So we have I times minus I, that's just a 1. Here we have a W, and the cotangent, the normal cotangent of a W. And that's nice, because we just put this in there, and we get the expansion. So here we have b to n factorial, and from this we get -1 to n. That's I to the power of 2n. And here we get 2 to the 2n times z to the 2n. I mean w. So in this way, we get an expansion for a cotangent. And now we could play with those expansions and get more and more for different functions by either integrating or just by messing up with those fractions a bit. And we could get expansions for instance, this function, or even for a tangent, or by integrating logarithm of this fraction or logarithm of cosine and such things. All of those things have expansions that contain Bernoulli numbers. And they can be quite simply deduced from this. But well, there's not so much time, so let's continue. We just leave the generating function here and now we can use that generating function to do something more, because when we just listed some of those Bernoulli numbers, it seemed that they are just some quite small and quite weird fractions, but that's not true at all. So we just can see that by doing an asymptotic expansion of those Bernoulli numbers, getting an asymptotic formula for them. And that will be very simple because we have this function and we have complex analysis. So how that does help us, let's see. So here we have a complex plane. Now, this function has a pole at every multiple of 2 pi I. So there are poles in each number of this form except for 0, because at 0, this is just 1 plus z plus whatever, and the ones cancel, so it has a value of 1 in 0, and there is no pole. But in all the other points, there is a pole. So here is a pole, here is a pole, and so on. And now, as we all know, if we do the series expansion, which just contains the Bernoulli numbers, then the series will converge only up to the first pole that the circle expanding from the 0 encounters. So in fact, it will converge in such a circle. And the radius of convergence will be just the distance to the nearest pole, which is 2 pi. And now we can start with the asymptotical magic, because we have the Cauchy-Hadamard formula, which tells us how to get the radius of convergence from the coefficients of the series. And you all know it from the basic calculus course. It looks like this. And in the basic calculus course, you use that when you know the coefficients and you want to get the radius of convergence, but we can use it the other way around. And we know the radius of convergence and we can just get some information about the coefficients. And so here it will be very rough information, but still it will be nice. So if the limit superior of this thing, which is, I will just wipe it out and put the concrete numbers in there. To vidět? To je asi nějaký. Nevím, jestli to není jenom košna už vypsaný fixy, s čím tady píšu. So if this is true, then it must mean that if the n is sufficiently high, then it's just larger than some uppercase n, then we must have this. This is less than 1 over 2 pi plus some epsilon. And of course, this big N and epsilon, they are just connected by the usual definition of the limit. So in fact, this means that if we take the nth power, and here's a factorial, then we have that Bn over n factorial should be less than, and here I will just say it's less than some constant times 1 over 2 pi to the power of n, because this epsilon can be really made as little as we want.
Don't you want an absolute value?
Oh, I couldn't understand what you want.
Don't you want an absolute value around Pn?
Oh, of course. Of course. I mean, it should have been here as well. Thanks. So this is very rough, but already this tells us that Bn over n factorial is O 1 over 2 pi to the power of n. And that's just information for free. We did nothing, next to nothing. And yet we get such a nice result. But of course, what if we want something, let's say, a little bit more precise? Well, then we will just repeat the same trick. But if it works by just having the radius of convergence here in that power, then the simplest thing we can do is just making the radius larger. And how to make it larger? Well, just let's eliminate these two poles. So if I take the B and I subtract the principal parts of this function in those two poles, then the result will not have poles in those points. So the principal parts are just, well, you can pretty much see that this only has simple poles. And so it's just a matter of calculating the residue. And we can do that very simply because in 2 pi I k, we get here the z just stays and we can plug in, and here we take a derivative and plug into the derivative. So the derivative was e to the z, and we plug in this. However, the k is an integer, so this is a 1. So this is the residue in each of those poles. So this has the principal part of 2 pi over z minus 2 pi, and this has minus 2 pi over z plus 2 pi. So let's get rid of those. I mean 2 pi I, sorry. So I subtract that one and this one. So now let me just simplify a bit. So I will want to divide by this 2 pi I here and here, just to get some geometrical series that will be very easy to expand. And here I would get z over this thing minus 1, and I would like it to be the other way. So let's do it like this. And here I will do just the same thing. I mean 1 plus z over 2 pi I. So this is the function with those two poles removed, and that has the radius of convergence, not 2 pi, but 4 pi. And the best thing is that we can expand this into power series in a very simple fashion. So we get here z to the nth, and here. From the b, we get bn over n factorial. From this is just the geometrical series. So we get powers of z over 2 pi I. And the zn to the nth is already in here, so we get plus 1 over 2 pi I to the n plus 1 over minus 1 to the nth, because there is a plus here, 2 pi I to the n. So if we just simplify that a bit, then we get bn plus, and here I to, let's see, here we have 1 plus minus 1 to the nth. If n is odd, then this will cancel. So this will just be here only when n is even, and that means this will be a 2 instead. And now we know that, oh, sorry, here is factorial. And now we will just repeat the same trick as before. So here we have that this coefficient, bn over n factorial, plus 1 plus minus 1 to the nth over this. After doing just the same trick with the Cauchy-Hadamard formula, we get that this is 1 over 4 pi to the n. So we have just obtained a factor of 1 over 2 to the n. So this is just much more precise than the previous thing was. And here we get just what we should have. I'm sorry. Here we have the real thing, and this is just estimate on the error that we are making. So what we get here is that if n was odd, then this is 0. So we are just getting 0. And if n was even, then we are getting something like I to the 2n, which is just minus 1 to the n. I will just write some k here. And here we have 2, because 1 plus 1 is 2, over 2 pi to the 2k. And here, if n is 2k plus 1, and here if n is 2k. And we need to add the error term to that. And here we obtain a very nice asymptotical formula. And this is such a really good formula that it even holds, I don't know, if you calculate B5 or B6 with use of this, then you get an error just like 10 to the minus 5 or 10 to the minus 6. So this is just a really, really good approximation. And we have that for next to nothing. We did no real work, just some subtraction of simple principal parts and some geometrical series. That's almost high school math, right? No trickery needed. Everything is very simple. There, I should have this. And so we now can see that, in fact, the Bernoulli numbers can get very big. And they can get very big quite fast, because this is bn over n factorial. So if we see what the b2k should be, there we get this thing, and here we get some 2. There is 2n factorial over 2 pi to the 2n. So it's quite clear that when we have 1, 2, 3, 4, up to 2n in here.
Okay.
Oh, I'm sorry. And only 2 pi, 2 pi, 2 pi in here, the factorial will get much, much bigger. And by the way, this expression is really not that good because, well, when we multiply this error 1 over 2 pi to the nth power by the factorial, we get something that blows up. So the error will be blowing up as well. And it's just the same thing that we get with the Stirling's formula. The Stirling's formula has the relative error going down, but the absolute error is just skyrocketing. But that doesn't mean that this is some useless formula. This is very precise if we keep the factorial here in the denominator. So it will be almost time to end this. So I will just want to do some. Okay, I will just proceed with doing this, and we will see at least one nice thing that I would like to show otherwise, but there will be no time for it. So now, oh, I shouldn't have wiped out the image, but too late. So now this we get when we eliminate the two poles at 2 pi I and minus 2 pi. And when we continue with this process, we can just do it again and again and get rid of those poles at 4 pi I and 6 pi I and so on. And since we already calculated the principal parts, they are always just 2 pi k I over z minus 2 pi k I. And now if we do this again and again, then we just get more and more terms of this form. And finally, we will get that bn over n factorial should be equal to minus 1 to the k plus 1 times. And now we just get the 2 and the pi to the, oh, I'm sorry, I just messed up again these things. I want the 2k in here. And here we get just a sum of terms that will look just like that. And from 1 to infinity, let's say, when we just get rid of all of those poles. And here, when we got rid of the poles at 2 pi I, we got 1 over 2 pi to the power of 2k. And when we will get rid of the poles at 4 pi I, we will get just the same term, only with 4 pi. And then with 6 pi and so on. So what we get here is just 1 over 2 pi to the 2, oh, I mean to n, of course, because the pi is over there. And now we just got this sum here. And if you remember what I was writing, just to see if there is anything to be seen on the whiteboard, well, we are going to prove that. Because here, we can just take out the 1 over 2 to the 2k. We have 2 over pi to 2k, and let's get rid of that 2 as well. Here we have the sum 1 over n to the 2k. So now if we express that sum, one over n to the 2k, then we get minus 1 to the k. Here we get b to k over 2k factorial, that was on the left-hand side, and then we get 2 pi to the power of 2k over 2. So in this way, we can calculate all of those sums that will be otherwise very hard to do exactly. And just to see if that works, let's try a few of them. So First, the one that everybody knows. So let's use k equals 1. So those minuses cancel. Here we get b2 2 pi squared, and here we have 2 factorial times 2. Now, we have b2 is 1/6. And here we have 2 squared, that is 4, and 2 times 2, that's 4 as well. So we get that famous result. But that's not everything. We can continue. Here we get minus b4 2 pi to the 4th power 4 factorial times 2. And now you can say, wait, what? The minus sign, but the b4, in fact, is negative, and it's the minus 1/30 that we encountered before. So these minuses actually cancel, and we get, here we get 16 pi to the 4th over 30 times 2 times 24. Now, 16 over 24, that is 2/3. Let's get rid of those 2's, and we get pi to the 4th over 90, which is the correct result, of course. And I think that many people just know those by heart, but what about the next one? Here we get a plus. And here we get the 6 factorial times 2. So here the calculation will be pretty rough, let's say, but b6 is 1 over 42. So here we get 2 to the 6, pi to the 6, and here we have 8 times 9 times 10, and times 2 as well. And then we have the 6 times 7. So 2 to the 6th, and here we have to the 4th, 3rd, 4th, 5th, 6th. So we got rid of all of those 2's. And now what is remaining is 9 times 5, which is 45, times 21, which is 900 plus 45. So we get the result pi to the 6th over 945, which is in fact correct. So in this way, we can calculate just about any of those sums. And these are, as we can see, very connected with those Bernoulli numbers. So that's nice. And since it's time to finish, then let me end with a little joke. So we remember the generating function of the Bernoulli numbers, which was just z over e to the z minus 1. So now, if I just multiply by e to the minus z, we get this. Let me change the signs. Let me use the geometrical series. Now we can expand those exponentials as well. And of course, this is a joke. So if you don't like these calculations, please don't fret. It's just a joke. So we have this, and now we can do just this expansion of the exponential. So here we get minus 1 to the k, I mean, n plus 1 to the k, z to the k over k factorial. So if we look at, and now here we have n plus 1, and it's going from 0 to infinity. So just do this from 1 to infinity, and here let's just have an n. Now let's exchange the sums a little bit, and we get something pretty funny. We get minus, I wanted to exchange them, of course. K equals 0 to infinity, minus 1 to k, z to the k plus 1, because there was a z in front. Here we have just this. So of course, this doesn't make any sense, but let's be honest, right? We all know that sum of all natural numbers is in fact minus 1 over 12, right? So if we want to know that, we just need to look at the second power here. And the only thing I did was just massage a little bit this generating function. So we know that that has to be equal to b2 over 2 factorial. That's the coefficient at z squared. And here we have minus, and the minus is a plus 1 over k factorial. Oh, of course, we have another minus from, maybe I did, oh, of course, I did a sign error in here. When I took this away, I should have done this. So this sign shouldn't be in here. Let's get rid of it. Now we get that answer. Here we get sum, and since b2 is 1/6, and the k was 1, then we have it. And of course, this was a joke, right? And this just came to be because this series manipulations were very fishy, and the series actually diverged. And so we got the sum of all natural numbers was minus 1 over 12. But of course, even if this is a joke, it has something real under the hood. And that's the connection between the Bernoulli numbers and the zeta function. And as you can see, what we did before, it was just evaluating the zeta function in some very specific points. And of course, there is the zeta functional equation, which makes it possible to calculate the values on one side of the real part equals 1 line and calculate them from the other side. So it's really no wonder that the Bernoulli numbers made an appearance, but yeah, this is how we can prove that the sum of all natural numbers is minus 1/12. And well, let's end with that joke. Thank you. I hope you had some fun, and that's it. Thank you.
Do you have any questions from
Yeah.
the audience? I mean, from the online audience?
Oh, yeah, I should tell you that if you have some questions, then of course, feel free to ask. Well, it looks like there are none, so maybe let's end.
You can ask. So you showed us the a few ways in which the Bernoulli numbers appear. There's like some other parts of mathematics or physics in which they also appear.
Yeah, there is actually one way that I wanted to show, but there wasn't really time, but maybe I can do it just in a lightning quick fashion. So if we connected those finite differences to derivatives, it was kind of formal, right? It looked similar, but in fact, if we take the derivative as an operator that will shift a function, an infinitesimal amount of, well, of that argument of the function, then if we just exponentiate, then of course we take the infinitesimal operator and make a finite step out of that. And by the way, if we do this exponentiation and write it as a series, then we get just 1 plus 1 over 1 factorial d dx plus 1 over 2 factorial d dx second derivative and so on. And as you can see, we are getting the Taylor series, right? And that's really nothing that would surprise us because, well, Taylor series is exactly what this does. We just take the function and step a little bit to the side. But when we have this thing, then we can also write a finite difference. So if we take this, we know that it's fx plus 1 minus fx. But we can write fx plus 1 with the use of this operator. So we have this acting on the function minus the function itself. So if we do that, we just have the operator e to the derivative minus 1, and that's exactly the finite difference operator. So we can write this. Maybe a bit peculiar, but it's in some sense true. And when we have this, well, let's make an inverse. So the sum is just inverse of this. And now this is still quite fishy, right? But it's what's at the heart of what I will show. We already know how to expand this thing because the generating function of Bernoulli numbers was just z over this. So after just getting rid of that z, we will get exactly what we want. So this is, in fact, 1 over z. Let's write it like this. And then what's there is sum from n to infinity. Here we have bn over n factorial and d dx to n minus 1 because we divided by that z. So here, well, the inverse of the derivative is an integral. So let's write it like that. And here, the 0th derivative, that's just the function itself. So here we have just 1/2 because oh, there should be a minus because the b1 is minus 1/2. And then we just have the rest. And what we are getting here is exactly, oh, need to get rid of this. The Euler-Maclaurin summation formula, right? Because if we put limits on this, then we put limits on everything in here, and that will just give us what we know as the Euler-Maclaurin summation formula, which is something like this. We just integrate. Here we need to put the limits from a to b. And we use this on some function to be concrete. So here we have the function integrated minus 1/2 of the function. And we need to do that in the limits. And then we have this. Here we have the derivative in one endpoint minus the derivative in the other endpoint over, well, over nothing. And this is the Euler-Maclaurin summation formula. And well, this is how the Bernoulli numbers pop up in everything, because they are so tightly connected with all the sums, right? So just every time you happen upon those Bernoulli numbers, well, there's maybe some sum around from which they are coming. So that could be a partial answer to the question.
Do you have any other questions?
Yeah, any other questions?
Okay, so if not,
Everything's silent, so.
let's thank the speakers again.